Okay, so we've got a scatter plot with some time in hours and depth of water in feet. So I'll first review how to enter data. So on your home screen, hit Stat, Edit. If there's things in your list, you want to scroll up to L1, hit Clear, and then scroll back down, and it should be all gone. So in List 1, we're going to plug in hours, 2, 4, 8, 14, and 20. And into List 2, we're going to go with 44.7, 36.8, 29.2, 22.3, and 15.1. So once you get those, you want to make sure your scatter plot is on, so second y equals, and that brings you to stat plot. You want to make sure your first one is on. You want to make sure it's L1, L2 for x and y. If you do ever need to change L1, L2, down here above 1 and 2 in blue. Once that's on, you want to set your window accordingly to your points, which is going to change every problem. And in this one, our x's go from 0 to 20. You can go from 0 to 25 if you want. And our lowest is 15.1, so we could go 0 to 50, and we would cover all those depths on our y. So 0 to 20 hours on our x, and 0 to 50 for the depths on our y. So if I put that in there, I have a scatter plot, and it's telling us specifically on this one to run an exponential regression. If I go to my y equals, I have something in there, which is why I had that random line across my screen. You want to get rid of that. So run the exponential regression. Stat, calculate, exponential regression, list 1, list 2 for x and y, and go ahead and copy this down. It says round to the nearest hundredth. So that would be y equals 47.97. So that's my A times your B is 0.94 to the x power. So just making connections. There's a decay of 6%, which we can see, and that this was going downward. And then it wants us to use our equation to predict the depth of water after 2 days. 2 days would be 48 hours. So we're going to use this to predict second trace value at an x. Oops, just kidding. I don't have the equation in there. I just need to plug in 48. 47.97 times 0.94 to the 48th power. There's our 2 days. So round your depth to the nearest tenth of a foot. 2.5 feet would be the second part of your answer. How would you characterize the strength of the exponential correlation between the two variables? So you would want to look at your R value for that. So when I did my regression, I don't remember seeing an R value. I just don't think I was paying attention. I do have an R value of negative 0.999. Since R is 996, we'll go. Since R is pretty close to 1 or negative 1, we would say very strong, since this is close to negative 1. The negative 1 versus the positive 1 are both perfect correlations. It's just in a negative 1, it's an inverse relationship, meaning as one variable is increasing, the other one is coming down. That's all the negative 1 versus the positive 1 means. 16 jumps into one of the reading stats problems. So a survey of 40 high school students is done to determine how many of them like fresh fruit. So that's our sample size. The school will offer a fresh fruit option if more than 30% of the students like fruit. Well, that's going to be hard to tell exactly because we're only taking a sample of 40, but we will see that of our 40, 9 liked fruit. So 9 out of 40 on your calculator is 0.225. That's certainly not the 0.30, but again, this is just one sample, so we could have gotten unlucky. So our simulations were done with a population proportion, so assuming that the school was going to be 30%, how likely was it that we got this unlucky after 100 simulations? So 0.225, here's 0.225 0.22, 24, 26, 28. So 22 is here. 24 is here. So probably that bunch right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of the 100 simulations. So the observed sample proportion they asked for is the 0.225. Rounded to the nearest hundredth is 0.23. How likely is it, based on our simulation, that a sample size of 40 would have 9 or fewer? So that, again, so if we're rounding to 0.23, we'll say that this is 0.23 as well. So it's right in the middle of 22 and 24. So this is 20, 22, 24, 26, 28, 30. That makes sense. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's a 14% chance that we could have gotten that unlucky. So as far as confidence interval is, that's still probable enough, right? If it's less than 5% chance, you're outside of that 95% confidence interval. Less than 2.5% chance, you know, but again, it can go either way, but based on the simulation means definitely mention a percentage. So 14% chance. That's it. Say no more. Based on this survey, should the school conclude that they should not serve fruit for lunch? No, they shouldn't conclude that yet. There is a possibility that there is a 14% possibility, actually, to be more specific, that 0.225 was simply unlucky, meaning due to sample variation, the fact that they only took one sample. It doesn't ask you to elaborate and say what they should do, but if they did, for example, you could say something like they should repeat the study and do it a second time and do it a third time, and then maybe average all of those proportions, and then they'd have a better feel for the population. Would be a good follow-up answer to what they can further do to explore this. Number 17, a population is normally distributed with a mean of 164. Standard deviation of 18.65, we could label above and below if we wanted to. Sample size of 50 was taken from this population. What is the probability its mean would be greater than 168? So wherever 168 might fall, we're looking for the chances of something being greater than 168. This is a norm CDF question. So second variables where we find norm CDF. The lower is 168, finding the area of the shaded region. Upper is 99999. The mean is 168. The standard deviation 18.65. So there's essentially a 50% chance. So 49.999 would be 50.0%. Your norm CDF numbers were 168 is the low, up to 999, mean 164, standard deviation, and you do want to show your work, God forbid, in case you just happen to hit a wrong button and we know where those numbers, but what you intended on plugging in anyway. Okay, in a recent experimental study, 40 participants were broken into two groups. Group 1 maintained regular exercise. Group 2 maintained the same exercise regime but also drank a cup of green tea. So they exercised the same. So that was the variable we were controlling, was their exercise. The second group drank a cup of green tea each day. So I think what we're trying to figure out is, does drinking a cup of green tea help lose more weight? So Group 1, which was no tea, lost 5.3 pounds on average. Group 2, which took tea, lost 3.3 pounds more. Was that coincidental? Could it have been coincidental? Of course, it always could have been. How likely was it, though, that it was coincidental? Or how likely was it that there was kind of a strong correlation here with the green tea drinking? So you always observe the difference between your observed difference. So the observed difference was 3.3 pounds. Explain the meaning of this calculations in terms of this experiment. So on average, Group 1 lost 3.3 pounds less than members of group 2 who drank tea. Nothing overly creative there. The weight losses from the 40 participants, so now we're taking all the 40 participants and we're randomly shuffling them into groups, separate groups, and recording the difference over and over and over again between the groups. And this is what happens when they're randomly split, not split accordingly to T or no T. And so 3.3, here's 3, here's 3.5. So 3.3 is right around this spot. So of our, how many simulations? 100. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9% of the time, it did happen that there was a weight difference of 3.3 pounds or more, simply due to chance. So how significant is the induced treatment variability? So there's a 9% chance the 3.3 pound difference was coincidental. Because 9 out of 100 times it did happen that much or even more coincidentally. Was coincidental. Which means if you want to say it the other way, like glass half full, glass half empty, you say there's a 91% chance the 3.3 pounds was induced. In other words, caused by the fact that they had tea. And that's good for that. In number 19, a recent survey of 500 people, 45% of them reported that they were voting for candidate A. The survey was reported to have a margin of error of 2%. So 45% plus or minus your margin of error. Explain what this means in terms of the actual support. So with 95% confidence, we think the actual support for candidate A will be between, because our sample is all that told us it was 45%. The population is probably going to be somewhere around there, but not right exactly that. So as low as 43%, 45 minus the 2, and as high as 47%. If you have any questions, feel free to send me a remind text, but that kind of hits on just the style and the types of sentences you're going to have to write in your stats unit.